From, well, I haven't even lectured on that yet. For Friday? Yeah, today's Wednesday, right? Yeah. That's all right. All right. What's number? Which problem is it? I don't remember. So it's ln of x minus 4 plus ln x plus 5 equal to 1. Oh, this is a good one. This is due tomorrow, right? Not Friday, tomorrow. Okay. Sorry, I'm wrong. I did lecture on this yesterday, but this is a weird one. Okay. We've done all of the pieces of this. You just got to be a little bit creative. All right, so here we've got an ln x minus 4 plus an ln x plus 5. So using the law of logs, since this is addition, I can rewrite this as ln x minus 4, x plus 5. And that's going to equal 1. Okay. Using the definition of logs, I know that x minus 4 times x plus 5 has to equal e to the first. So now I can FOIL this. X minus 20 is equal e to the first, or just e if you'd rather. E to the first is just e. So now I've got to put this in standard form. And now I have to use quadratic formula. Oh, they shouldn't be. Let's make sure. So your A is 1. The B is also 1. Your C is negative 20 minus E. So x would equal the opposite of B plus or minus the square root of B squared minus 4 times A times C. All over 2A. So it's a negative 1 plus or minus the square root of 121. Wait, no, 81 plus 4E. All over 2. So if I do the first one, a negative 1 plus, square root, 81 plus 4 E divided by 2, I get approximately a 4.293. So 2952, 2925. And then we would also have x is equal to a negative 1 minus square root of 81 plus 4. All over 2. $5.2925? Huh. It should be right. So I'll do a little bit of a deeper dive. If you don't mind, if you've got it up, hit the Ask My Instructor option. And then I can take a look at what they have for the correct answer and see what happened. Okay? But yeah, I got the same answers you did. Well, we'll figure it out. Okay? All right. Anything else? Anyone? Anyone? Bueller? Shayna, did you have any other problems? No, this is yesterday. This was a part of yesterday's lecture. Yeah. I mean, we didn't do this exact problem, but we did problems like this one. Okay. All right, Ben, anything else? Okay. All right. Then we're going to start today with 4.6, which is modeling with logarithmic equations. Nope, that's not it. Yeah, okay. Or with exponential functions. Okay, sorry. So today we're going to take a look at some exponential growth functions. And there are two base functions that we want to use. The first one is when you are given a doubling time. So if the information you're given is that it takes 3 days to double, for example, right now when we talk about the infection rates of the virus, when we talk about flattening the curve, part of what we're talking about here is exponential growth. That if everybody was allowed to go and just do as they wanted, then the number of infections would double every 2 to 3 days. That's an exponential growth model. When we talk about the doubling time, by flattening the curve, what we're doing is instead of doubling every 2 to 3 days, it's doubling every 5 to 6 days or 6 to 10 days, depending upon your area and where you're at. So when we talk about doubling time, this is an exponential growth formula where we have n at t, or the number given time, is equal to n sub 0, the initial count, multiplied by 2, because we're doubling, the number of, or the amount of time, over a. Now again, just so we're clear on what each thing means, n of t is the number based on time. So the number of whatever it is we're talking about, infections, the number of bacteria, the number of carbon atoms based on time, is equal to n sub 0, which is your initial count or initial population. T is the time. Now, time can be any measurement: days, months, weeks, hours, minutes. and A is your doubling time. So is it 5 days? Is it 10 minutes? Then if it's 5 days, then your A would be 5. If it's 10 minutes, then your A would be 10 minutes or 10. Both A and T have to be the same measurement of time. So you can't say it doubles every 10 minutes and then give your time in hours. You'd have to convert one of those so that they were the same units. There is an alternative formula for when we're not talking about doubling. This is known as the relative growth rate. And it is a slightly different formula. N of t, or the number according to time, is equal to the n sub 0. Because it's not a specific base, we use the natural log here, e to the rt. Where n sub 0 is again our initial population. T is our time. Again, any unit of measurement. And R is our relative growth rate. Questions? All right, so a couple of examples here. First example. A bacteria culture has 25 spores in it and doubles every 5 hours. Three basic parts to this problem. First part is to find the exponential model. Or the number of cultures or the number of bacteria, let's say, after t minutes. Second part, estimate the number of bacteria after 18 hours. And part C is determine how long it will take to reach 1 million cultures or 1 million bacteria. Okay, so this is a problem of exponential growth. The fact that they used the term doubles every 5 hours lets me know that I am using the doubling time formula for this exponential growth. That is n of t is going to equal n sub 0, 2 to the t over a. I just need to determine what is my initial population and what is the doubling time. So that means that this 25 spores is my n sub 0. And since the doubling time is every 5 hours, that's my a value. So my formula is n of t is equal to 25 times 2 to the t over 5. Now, I would point out that t over 5 could also be written as 1/5 t and as 0.2 t. So if you see that in any of its variations, it's all the same. It's just some are more common than others. Part B says to estimate the number of bacteria after 18 hours. So what they're telling you is that T is equal to 18. So N of 18 would be 25 times 2 to the 18 over 5. This is just a plug and chug. Familiarity with your calculator is what's going to help you here. 25 times 2 to the, I'm going to do 18 divided by 5 right there on my calculator. And I get 303 bacteria. So after 18 hours, not quite a day, there would be about 303 bacteria. Questions so far? Okay, good. The third problem asks us how long it will take to reach 1 million bacteria. This is telling us that 1 million is our answer, or that N of T is going to equal 1 million. So 1 million is 25 times 2 to an unknown T over 5. I need to use what I've practiced with the laws of logarithms in order to solve this for T. This is the exponential function, and I now need to solve it for T. To do that, I need to get the base to the exponent alone on one side. So I'm going to divide both sides by 25. That tells me that 40,000 is 2 to the t over 5. Now, I like to use the natural log really just because I'm lazy, and I would prefer to write 2 letters rather than 3. Now I can take that t over 5 and move it down front. And in order to solve this for t, I'm going to need to multiply both sides by 5 and divide by the natural log of 2. This gives me my exact answer, which when you're asked for a specific time is not going to be helpful. So I am going to need to use the calculator. I'm going to do 5 times the natural log of 40,000. And then I'm going to divide that by the natural log of 2. And I get about 76.4 hours is my time. So it'll take a little over 3 days to get 1 million bacteria. Questions on any of those? All right. So then the second example isn't going to be the doubling. The second example is going to be the relative growth rate. All right. So let's say a species of bird was introduced 25 years ago. The initial population was estimated at 54 birds. The relative growth rate is 12%. Part A says find a function that models. Part B asks for the current population. And part C says how long until there are 2,400 birds. Okay. I know this seems a little crazy, but it's actually not that far out there. Do you guys do you know about the parrots in California? Okay. In the 1970s, there was a shipment of exotic parrots that broke open on a container ship, and 50 some birds were released into the wild of California. These are birds that were normally in like the jungles of Belize. So very pretty parrots that they were going to sell as exotic pets. So there's now this whole bird population that lives in California. I can't remember where. There's a Netflix documentary on it someplace. But there's this whole population of parrots that normally live in like the Amazon forest that are being supported in California. 50 years. It is. It's a little weird. All right. So use the words in the word problem. Do you see how it says the relative growth rate? So this is what tells me that I'm going to be using n of t is n sub 0 e to the rt. That gives me that information. The initial population, or n sub 0, is my 54. R is the relative growth rate of 12%. So I'm going to do 0.12, and t is time. Right? That's my n sub 0. This is my r. I think the piece that is often of interest here, many of you know already, but we'll say it again, is that percent should be written as a decimal when you put it into your equation. Okay? Now, I should add this. This should say 12%, and maybe I just didn't write it. That should tell you the condition of time, right? 12% per year. If it doesn't, assume we're talking about years. I should have mentioned that. Okay. So our current population estimate. Well, how many years have passed since there were 54? So this is going to be an n of 25. Because it was 25 years ago. So our current time is 25 years later. 54 e to the 0.12 times 25. (54) e to the 0.12 times 25. So I'm going to get 1,085 birds. Where's that one? There's this one. How long until there are 2,400 birds? Well, I'm telling you that this is your n of t, and you're going to have to find what t equals. I'm going to run out of room, I think. So we're going to have 2,400, yep, is equal to 54 e to the 0.12 t. So again, just like the last one, I need to get this e to the exponent alone. I'm going to divide both sides by 54. As a reduced fraction, this is 400 over 9, e to the 0.12 t. Running out of room. Right, so I'm going to take the natural log of both sides. Using my law of logs, that's going to be ln 400 minus ln 9 is 0.12 t. So I'm going to have an ln 400 minus an ln 9 over 0.12, which is an exact answer, but it's not helpful if I actually need to know how many hours or years or whatever. So I'm going to have to type this guy in. Ln 400 minus ln 9, then divide that by 0.12. And that will be years. Questions on that guy? All right. Okay. Great. So that's exponential growth. And so there are two other applications that we need to go through. And that is radioactive decay and half-life and Newton's law of cooling. So let's take a look at radioactive decay. You've likely heard of radioactive decay. We talk about this in terms of plutonium and the Chernobyl. Did anybody watch Chernobyl this spring, this past fall on Netflix? No. All right. Okay. Well, that was about Chernobyl, which you may or may not know about. It's a very interesting topic, but radioactive substances are toxic to us, and they decay or deteriorate at a specific rate based on each element. The rate of decay is proportional to the mass of the substance. So imagine you had $100. Okay. Let's do it in terms of money because that tends to make sense. You have $100, and each day you lose 10%. So after or on day one, you have $100. But day two, you have $100 minus 10% of that 100. So you're going to lose $10 and you're going to end up with $90. You've lost 10%. On day three, you lose 10% again, but you're not losing 10% of 100 now. You're only losing 10% of 90. This is 90 minus 9, leaving you with 81. On day four, you're going to lose 10% again, but you're only starting with 81. So when you lose 10% of that, that's 81 minus 810. So what's that going to be? 7290. Do you see how the loss is proportional to what you started with? Even though I'm saying it's a set amount each day of 10%, it's actually not a set amount because each day your base is going to change and give you a little bit less. Is that all right? Garrett, you might be the only one listening right now. I did. Oh, I didn't hear anybody else. I just heard Garrett. Okay. Sometimes it's hard to teach when I can't see your faces. Okay. Now, most of the time, we don't measure this in terms of a 10% rate. Most of the time, we measure this in terms of what's known as a half-life. How long does it take your money not to go down by 10%, but to go down by half? This is known as a half-life. What that means is if day one you have $100, then day two you would have $50. And day three, you would have $25. Do you see how it's going down by half each day? Okay, thank you. The formula for this, because it's not always simple days, is m of t is equal to m of 0, 2 to the negative t over h. Where m of 0 is our initial again, initial amount, where t is the time, and h is our half-life. And just like the doubling formula, the time and the half-life have to be the same measurement of time, but not necessarily always years. You can have half-lives in minutes, you can have half-lives in hours, you can have half-lives in years, seconds. It really doesn't matter. So if they give you a problem that specifically states half-life, then you can use this formula. Okay. Okay. If they give you I'm going to do this a little bit differently. Okay. Radioactive decay model. How much time do I have? 6 minutes. Oh, not a lot. Okay. All right. So the radioactive decay model says if they give you m sub 0 as the initial amount, and a half-life of h, then the mass remaining, or the amount remaining at time t is modeled by the function m of t is equal to m of 0 e to the negative rt, where r is equal to ln2 over h. This is the relative decay. Oh, I hate when I focus. There we go. It looks like an N, but that's an H. Okay. So here's what's going to happen, because I'm going to run out of time and we're not getting to Newton's law of cooling, which is pretty important. So I'm going to lecture on Newton's law of cooling tomorrow during class time. And I will also give Q&A time, but because this Unit 4 test is due next week, and I've got both Monday and Tuesday set up for Q&A on all of Chapter 4, so to finish anything up. I think what I'm going to do is mostly take Thursday or tomorrow, that is, just to wrap up lecture and take any last-minute questions on the homework. And then Monday we'll use for review, and Tuesday if you want, if you have any questions before you take the test. How's that sound? Yeah, it's like last time. Course of a couple. I want to say Tuesday morning and closes Thursday night. I can check. Hold on. Let me. This one time. There we go. Yeah. Oh, okay. We're going to be difficult. All right. Hold on. I'm just pulling it up to check and make sure my times are good. So, and of course, it's being particularly slow because I need it to go quickly. That's always the way it works, right? Schedule. There we go. Just want to see when I have it opening for next week. Up, 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 up. There we go. Yep, I have it opening Tuesday, April 21st at 8 a.m. and closing the 23rd at 11:59. There is also a bonus homework review from all of Chapter 4 that should currently be available. And that closes April 23rd at 10:59, so the hour before the test closes, just in case somebody's trying to do stuff in order. Okay. Oh, you did?